Things. All right. How'd you go with the memorizing of the reactions? So we are up to how many reactions did we cover? Up to 10
Yeah.
the reactions we did. So how'd you go with those?
Yeah, I think I memorized it all.
Good. Okay. So that means I can put you on test next week. We'll see
A
how it goes with
test?
that. Yeah, of
Okay,
course. And, we have to check it like whether you memorize them or not. All
sure.
right. So then we're gonna go through the so last week we went through like what chemical reactions actually produce in the alcohol. So that includes, but typically the reaction start is from haloalkane and alkene and glucose. These are the three main resources of them producing the alcohols. So those you need to memorize. Now, what we're going to do today is we're going to talk about how we then actually use the alcohols too. So, kind of related to a little bit of like some general content. So, if you want to test that, let's write it over here. I would call that this is the testing, testing for the alcohol. So, if you would like to know whether we have some alcohol presented or not, we are adding some like sodium NaS into it. And that alcohol, with the presence of these sodium metals, produce the hydrogen gas. There will be some hydrogen gas. So let's check that. So H2 gas is produced. So I'm gonna put that as equation. Hmm, what should I do? Yeah, I'm making the equation 11 like this here. So continue on to the from what we have done last week and copying this one there at the back. So equation 11 is the testing for alcohol, like under all the presence of the alcohols. In general, it requires when we have any type of the alcohols, which it could be a liquid or even for the aqueous solutions too, reacting with sodium metals, it is producing some hydrogen gas forming out of two and forming that into the salt. So, for example, we can think about ethanol that is giving us that two carbons related, two carbons, and with the one OH. And when this is reacting with the solids, which is the and what does it do is you're basically taking the hydrogen out and forming that into this sodium two attached on the side of the hydrogens. So we actually need two of those, and so it'll be forms like sodium will be attached to the position of the where the hydrogen used to be. So it look like this. We have the oxygen which is attached to sodium metals, and there's hydrogens. The times two of that release that two of the hydrogen, one of the hydrogen gas forms like this too. But simply, the way you can understand the point is, if you want to see like whether we have the alcohol presented or not, we just put the sodium metal, like probably the granule, like a powder of sodium, and seeing that whether this produce the hydrogen gas. And do you remember what test we need to go through the hydrogen gas? Hydrogen gas.
Or what test it is?
Yeah, we test for to test for the hydrogen gas because
Is it
when
the
you just see the gas comes out, it could be anything. So, yep,
is it the pop test?
it is the pop test. So we do the pop test to test for whether the gas is the hydrogen gas. In case we have the CO2, which is the carbon dioxide release, we have to go through the lime water. And in case we have the oxygen gas presented, like we assume there's oxygen gas, we put it into the naked flame or like something the matchsticks, see that it's producing some more of the brighter light or not. Okay, so that's for the alcohol to the hydrogen gas, the first reaction, the use of the alcohols. Then we have to talk about in put up like difference between primary, secondary, and tertiary alcohols. And this is something that very important. So let's start with the primary, secondary, and tertiary alcohol like this. Do you know like do you remember the difference between primary, secondary, and tertiary alcohols?
No, I don't remember.
Oh, it's a very important one. Showing you the difference between primary alcohol. So the one dash. Simply primary. Okay, I lined it up here. Secondary alcohol and tertiary alcohol would be look like this. what we have to look at is we are looking at the carbon which is attached to the OH. There's a many names for that, but I just generally give a name this as my prime carbon. I call that as prime carbon. So in the perspective of prime carbons, we're going to count that how many carbons attached to the prime carbon. So if we have one, and if the rest is the hydrogen look like this, so sometimes I put it into the all, which is the kind of chain of the carbons. This is called the primary alcohol. So as you can see that like that prime carbon is only attached with one different highlighter color, one carbon chain. It's showing you the what? Just the one carbon attached to the prime carbons. Following to the definition of the primary alcohols, secondary alcohol would be the one with the two R and R dash and the hydrogen attached. So as you can see, there are two of those attached to. So example of the primary alcohol would be showing you that this, and Jenny, what's the name of this?
Ethanol?
This is ethanol. So is ethanol the primary carbon?
That's a secondary. Oh, wait. Wait, sorry.
Mm.
Wait, what was the question?
It's ethanol, primary
Yeah.
or secondary?
That's a secondary.
It's a primary.
Oh,
What do
whoops,
we have
sorry.
to look? We have to look at the carbon that is attached with the OH. How many now? Looking at the highlighted carbon, how many carbons attached to the carbon? How many like carbon chains attached to the prime carbon then?
One?
Yeah, that's why this is a primary carbon, primary like alcohol. Then drawing the structure of the secondary alcohol, it'll be look like this. We can have the alcohol structures that look like this. Name of this? Jenny, name of this?
Oh, sorry.
Name of this one?
Okay, is it methyl? Oh, sorry. Propanol?
Propan, just a propanol?
Propanol.
Propan-2-ol. So is a propan-2-ol primary or secondary carbon? Sorry, secondary like alcohol.
Secondary,
How do you know it's a secondary?
because the prime carbon is attached to two carbon chains.
Good. So we can see like prime carbon has two. Can you see like the one and two carbons attached to the prime carbons, whereas ethanol just has one carbon attached here. Tertiary carbon will look like this. We can have a structure of OH, and it will be attached with three carbon chains. Can you see that? How it is attached now? They're looking at the prime carbons. You're to see that there are three carbons attached to it. So this is what we call the tertiary alcohols too. So it's very important to know the difference between primary, secondary, and tertiary always, because by understanding that, you understand like what's the chemical reaction difference between three as well too. Any questions up to here? Nope. Okay. Now, why we have to talk about this? Because each of the primary, secondary, tertiary alcohol, when they go through the oxidation process. Now, think about the meaning of the oxidation that we learned in year 11. Oxidations in general, when I said the oxidations, so an oxidation in general is basically losing electron. It's the general term that we learned and we used in chemistry too. But another way we can think about the oxidation is it is the addition of the oxygen into it, or addition of or it makes that the losing, as a result of that, losing on high H plus as well forms too. So it depends on the primary, secondary, tertiary alcohols. They will have go through different chemical like reactions. They will producing different products. But very important is super important to understand, and you need to memorize that the oxidizing agent that we commonly use are something H2SO4, which is known as sulfuric acid, plus we either use potassium permanganate, which is the purple color solutions, or H2SO4, which is, or like even sometimes we H3PO4, H3PO4, which is phosphoric acid, with the potassium dichromate is something that we use. And potassium dichromate is known as, let's double check, as far as I remember correctly, it would be the colors of the orange. Just double check. In a while. It is the color of, I was right. Okay, yeah, orange. So I would say that's colors of orange. I sometimes describe the yellow color as the color of the potassium dichromate. Do you think you need to memorize them all? You do need to
Oh,
memorize them.
okay.
You do need to memorize them as in terms of the color, as well as actual oxidizing agent that we use, and what are the products that produce too. So in general, when we're writing the chemical reactions of the oxidizing reagents, we write it like this. We put the reactant on that side, and on the product will be provided like this. We put a single arrow for the oxidation reaction because it's simply not reversible. Time to times we use all the full details of the chemical, like the catalyst we use. So we may use right like this H2SO4 slash K MnO4 with the potassium permanganate, or we sometimes use H2SO4 and K2 Cr2O7 in forms too. So you need to write it down all the relevant all the relevant catalysts as well as the oxidizing agent on the top of these single arrows. Another method that we can use is because I can't write sometimes it's too long to write all that chemicals. So we simply just write it as H plus, which is representing like the strong acid or any of those acids that we're using for the reactions, with just a manganate minus, or we may just say H plus with Cr2O7 2 minus forms like this. Okay, this is what we call that as acidified permanganate. And this has also been known as acidified the dichromate. So we're using either this, the acidified permanganate, or using the acidified dichromate on both. So let's move it on to the actual what experiments we do. So it's very important to understand and memorizing them too. I showed the actual reactions of the primary, secondary alcohols too. So for the primary alcohol, I go in this order here like this. For the primary alcohol, when this go the oxidation, we're using the H plus Cr2O7 minus, or we either use H plus MnO4 minus like this. Now, as a result of the oxidizing the primary alcohol, so I just put the 12 reaction, 12 oxidations, there will be a product of aldehyde produced. Now, Jenny, what's the aldehyde?
Um, isn't it like a carbon atom that has like a double bond with an oxygen atom and a
Yeah.
single the hydrogen atom?
Yeah, so basically it's the one of the functional groups in the carbonyl groups, which has a carbon double bonded oxygen attached, and there'll be hydrogen attached at the next two. Good. Now that aldehyde can go through another oxidations. I just write it like this. So 13, the another oxidation, but this time the oxidation we use the same H plus, the oxidizing agent, Cr2O7 minus, or H plus, MnO4 minus, plus we actually put a bit of the heat to get that. As a result of that, what we're getting is we're getting the functional group called the carboxylic acid, which it forms like this. So I show the reactions at the back page. I'll move to the back page numbers. Okay. So this is equation 12 and 13. So move it at the back. 12. So oxidation of the primary alcohol. So I give you an example of this. Primary alcohol, like typical example is the ethanol. So we have ethanol, which is, can you see like this is Y, the primary alcohol now? Yep.
Yep.
Yeah. So if this going through the chemical reaction, going the oxidation, so the very important to put the correct oxidizing agent on the top. So we put the H plus Cr2O7 2 minus, or you may just say H plus MnO4 minus like this. It doesn't matter like which one you put it into. Then what you be able to see there is this is creating forming. So what it actually does do is here. This whole things will be removing this hydrogen. So it will be directly targeting this hydrogen over here and making this the oxygen to be more open, or like I would say the radical stage. You don't really need to know how the process of that too, but you can just simply understand it as whenever we go through the oxidation reaction, the oxygen is removing the hydrogen as they get oxidized. It's making more like oxygen solely forms too. So as a result of that, this is a resultant forms. We have, instead of the alcohol functional group, can you see like there's a forming the carbonyl double bonded? And the remainder would be simply the same as that too. Oh, sorry, removing another hydrogen, so I have to remove another one in here like this. Could you see like there's two things removed? There are two hydrogen removed from the oxidizing, oh, maybe adjacent over here like this.
Yep.
So as a result of that, you can just write it down as two. As a result of the oxidation, one hydrogen attached to the carbon with oxygen is removed. So what do we now have? From this ethanol, we now have the ethanol is produced. So ethanol is now become to ethanol. This is something what I call as the first oxidation of the primary alcohol. And this can actually go through the another chemical reactions too. So that's a reaction 13, reaction 13. So we can make just like oxidation of the aldehyde from the primary alcohols. So during the structure of the aldehyde here, again too, that's the aldehyde we produce from the ethanol. Basically, it goes through the same reaction as this. H plus, oh, thank you, Ria. Okay, thank you. Sorry. H plus and Cr2O7 minus, or even we can use the H plus. We can use any of those two. It doesn't really matter. But importantly, we have to put a little bit of the heat because that's it requires a bit of more like activation energy to proceed the reactions. Jenny, have a look at this carbon here, the prime carbon. Okay, how many hydrogens attached over there?
One.
One. So that has potential to go be further get oxidized, means that we can add it up the another oxygen to the carbon. So it's very interesting to see that what happened next. We still keep the carbonyl with the next methyl attached to the carbons, but this will now have this kind of alcohol be reattached. And the name of this is known as ethanoic acid is now produced. So time to times we are showing the reaction kind of in the same manners too. So we may think like in the reaction type as this. We just put it like, oh, not this one. Let me just copy that again. In the case of we have to show the oxidation of the primary alcohols, time to time we're showing the reactions like this. And what is missing here is we have to put a heat on the top of that too. So an example of that is we use a butane 1-ol. Butane 1-ol can go through the oxidation reaction using the acidified by oxidizing agent, becoming the butanal, and going through further oxidation using the heat and acidified by oxidizing reagent and butanoic acid too. Time to time show the butane 1-ol, the butanoic acid straight away like this, using the same agent of the H plus Cr2O7 to minus with the heat. But heat is not always the mandatory, like always not always the compulsory, but it's good to write it that this is actually the chemical reaction of the oxidation of the butane 1-ol. Any questions for this? Okay, so that was the first reaction of the primary alcohol. So let's move back to now this time the secondary alcohol then. All right, the secondary alcohol can go through another oxidation reaction. So it will be like this. We can have question 14. Oxidation here again. And it's basically using the same agent, H plus and Cr2O7 to minus, or either H plus potassium permanganate, SG2. Then you'll be able to get from the oxidation of the secondary alcohol, we're getting the ketone is now produced. Okay, so quickly showing what reactions of the secondary alcohol in the back pages too. So let's move back to the back. Question 14, equation 14, sorry, 14. Oxidation of the secondary alcohol. Okay, example of secondary alcohol could be like, I can draw the butane to ol, look like this. Now, can you spot that why this is the secondary alcohol, Jenny?
Because it's attached to two carbons.
Yes, the prime carbons, which is with the oxygen, which is with the hydroxyl, is attached with the two carbons adjacent to. So this is how we define the secondary alcohol all the times. Going through the reaction now, it doesn't really require the heat for this. So what does it do? You use the same agent, H plus Cr2O7 to minus, or you can either use H plus MnO4 minus. I just write it down everything just to make a habit too. Now, let's focus on to this carbon here in the green highlighted. Okay, what you'll be able to see here is that carbon has only one free hydrogen on the top. So we just count that as the carbon has only one hydrogen, free hydrogen attached to, means that it only has one chance to get oxidized, because as a result of the oxidation, it will removing this out. So let's see what happens then after. As a result of the oxidation then of the secondary alcohol, it becomes like this. We have 4 carbons attached. This oxygen of the OH is now becomes the carbonyl group, double bonded oxygen, and we removing the one hydrogen and just remainder will be look like this. The name of this is known as butan on is the name of this one. There'll be no butan 2 on. There's no point of writing the butan 2 on because there's only one type of butan on, and that is known as the oxidation of the secondary alcohol. Any questions?
No.
Okay, now showing you what actually color changes for this. Okay, first of all, when we're using the dichromate, this one dichromate over here, I can I write it down over here, the primary secondary alcohol. As a result of the using the dichromate, this is actually a color change we'll be able to observe too. So dichromate has kind of yellow color, and alcohol generally be in terms of the colorless colors too. So that's the primary color when we just simply adding the dichromate into the alcohols. What you can see there is, if we're adding to the propan 1-ol, and this color change, primary alcohol got color change to yellow to green, or the orange to green. Same for the propan-2-O. We have its color changing from the yellow to the green as well too. But what we'll be able to see from the third or the tertiary alcohol is it doesn't really change the color, which indicates that there is no oxidation happen for the tertiary alcohol. Does it make sense?
Yeah.
Now, it is very important to memorize the color change because sometimes like they give you the questions like, hey, we have like some unknown reactants, unknown like organic compounds. We put some acidified dichromate into it. There was a color change from yellow to green. So what could that be? That's another possible question that we can get in your standard too. Another example is using the permanganate. So remember that the yellow color is representing the dichromate. When we're using the permanganate, it will be look like this. So remember, like the permanganate is a purple color. So as you can see that the purple color is now from the permanganate. If that's go through the oxidation, we have seen the color change to the colorless. So propan-1-O, which is the primary alcohol, and propan-2-O, which is the secondary alcohol, will go through the oxidation reaction with the permanganate. Therefore, color will be changed from purple to the colorless. However, for the tertiary alcohol, there will be no color change from purple to purple, simply because there is no oxidation reaction happen. So that's why we can write it down on the tertiary alcohol part over here. There'll be no. So I'll just say there's no oxidation happen for the tertiary alcohol then. Does it make sense?
Makes sense.
Okay, now let's talk a little more about this one over here then, carboxylic acids. Inside the carboxylic acid, so if you remember, the carboxylic acid has a structure of the COOH. So quickly drawing the structure look like this, carbonyl with the OH. R is the carboxylic acid. Carboxylic acid can actually go through the reaction called the substitution reaction. So I can write it down as the equation 15, substitution of the using the NH3, which is ammonia. Of that too. As a result of that, ammonia will take a place of the OH, and as a result of this, we are able to produce something that's known as amide. Okay, so amide would be what? The carbonyl with the NH2 is attached to. So that's rare, that we rarely talk about in the year 12 standard, but it's good to know, the 15. So substitution of the NH3 on the COOH, it would look like this. If you have ethanoic acid, oh, sorry, that's not ethanoic acid. Need to remove that. Which is going through the oxidation reaction NH3 over here like this. We may be able to get some, actually to put the NH3 on here. It will forming the replacing the fusion of the alcohol into NH2 like this. But as a result of that, as the OH is removed with the one hydrogen, it's producing the byproduct of the water will be produced as well too. So that's how we can produce the amide from the given the carboxylic acid by using the ammonia gas or ammonia, or like aqueous ammonia. Okay, that's the equation, the formula 15 for now. And the last one that I want to talk about today for the use of the alcohol, and most likely this will be like for your exam conditions too, is when we have reaction between carboxylic acid, so I need to use that space, any of the alcohols, and that goes to the reaction called E16, that's known as esterification. And for the esterification, it's very important to memorize what condition required to. We're using concentrated H2SO4 sulfuric acid, and we also use indeed the reflux the system with a bit of the heat required as well too. And as a result of the esterifications, they are producing the ester is now produced. Okay, so let's talk about the last reaction, which is the alcohol reaction 2, reaction 16.
What's reflux?
Reflux is the system that I showed the example of reflux from the page. It's actually like a tool that we are using the condensers. So we're using the condenser to like capting like not like those gases get escape from the system or the apparatus. So I show you that by looking showing the picture of the reflux system. Here you go. It would look like this.
Oh, is it on there? Oh, yeah, there it is.
No, not this one. Ester, reflux system is something look like this. So we are gently heating up with using the electric heater or the water bath. As you can see, like we're using a condenser. Can you see like water's going in, cooling water goes in, cooling water out? Now, whole purpose that they're using a condenser, which we call the reflux system, is we don't want to the gas escape to the atmosphere because basically we're dealing with the organic compounds. And a lot of times organic compounds are highly volatile and is highly toxic if you inhale them too. So for the safety reasons, we don't really we don't want to like to escape to the atmosphere. This is why we're using the reflux system. We're basically cooling all the gases back into the volumetric flask. Therefore, we can just proceed the reaction. There are two purposes then. Okay. But let me just write it down the esterification whole process. I will tell you about why we need to use a reflux system as well too. This is can be part of your exam questions also too. So that's esterification. Do you remember the number of the esterification reaction? Was it 16?
Um, yeah, I think it was, yeah, 16.
16, thank you. 16 is esterification. Basically, what we do is we're using alcohol. It doesn't matter, like it could be any of the alcohol plus the carboxylic acid. And very important to remember that this is reversible, unlike the other chemical reactions that we discussed in the organic compounds. And for this reaction, we use very specific the agents. As I said, concentrated H2SO4, as well as we use in the reflux system. And we put some bit of the heat onto it. And as a result of that, there will be an ester produced and plus the H2O as produced as a byproduct. So let's talk about a bit more about ester. Ester. Ester is look like this. We have carbonyl with the O and R is something we call it as ester. R dash and R. So as you can see that it contains the bit of features of the carbonyl and some of the features of the oxygen as well too. I would call this is coming out from the some different like functional groups together too. So let's give it some example of this ester. I can draw like this. I can draw like one ester. They look like we have two carbons attached. And there'll be one carbons, just one hydrogen attached here like forms two. Okay. In general, I call this part after the oxygen of the ester is the tail of the ester. I mean, that's my word, but it's easy to memorize in this method too. I call the tail of the ester, and the one contains that carbonyl is called the body of the ester. Okay, so the way we can name this ester is basically we have to follow the rules of the nomenclature too. So start from tails, which has the suffix of the YL, and body would have a suffix of the ATE, no 8. So in terms of the nomenclature, if we have two carbons, it's always be, they follow into the meth and math, it'll be ethyl. That's coming from the tail of the ester. Now, time to name the body of the ester too. On the body side, we can only see the one carbons attached, so we just give it the meth. straight away. And then just put the suffix, which is the methane, AN. Remember the AN stands for the one single bonds only, and O8. Methanol 8 is O8 is how we name this ester 2. So ethyl methanol 8 indicates that we have a two tail carbons in the tail groups and one carbon in the body groups too. Does it make sense?
Yep.
Yep. So to produce the ethyl methanol 8, then we're able to produce by using the very specific alcohol and carboxylic acid. Now, the alcohol that we use to produce ethyl methanol is we're using an ethanol that look like this. And the one for the body part, for the carboxylic acid, we're using the methanoic acid that would look like this. Now, could you see like some similarity between those alcohol and carboxylic acid to the given ester?
Yes.
Yes. If you could find that, hey, this is the body of the ester. This was the tail of the ester too. So what you need to remember, understand that is the body of the ester is coming from it's producing the body from the carboxylic acid. So carboxylic acid basically containing the carbonyls becomes the body of the ester. And the tail of the ester would be from the carbon from the alcohols too. So when they go through the the esterification reactions, this is basically what happened. The OH, that OH, and both of the OH given here. Can you see the two OHs?
Yep.
Yep. When this go through the esterifications, this oxygen, the hydrogen, we basically get a help of the sulfuric acid. This is why we have to use this sulfuric acid. Now, sulfuric acid is known as the dehydrating agent. So when this going into here, it is helping the carboxylic acid to remove this part. So as a result of that, the whole thing's got to be removed. And then this OH is got to be attached with the losing the one out too. So can you see that? We have our OH is coming out from the carboxylic acid. We have a hydrogen coming out from that. Adding these two up, they're producing the one water molecules look like this. And the remainder part of the alcohol and ester is now joined together, or chemically bonded together, produce the ethyl methanoate forms like this. But very important to understand that this is actually reversible reaction. Now, thinking about meaning of the reversible reaction by understanding the what we learned in module 5, and this is why we need to understand the module 5 as well too. Now, reversible reaction means that there is a chance that the ester can be decomposed back into the alcohol and the carboxylic acid. So this is the reason why it's give a reason why we're using the heat first of all. As you remember for the some like the heat, the importance of the heat in the reversible reaction or the equilibrium. Do you remember that heat is increasing the rate of both the reaction side?
Oh, yeah.
Yeah, therefore we are able to get the more yield of the ester in the faster rate. Concentrated H2SO4. So I talk about some of the conditions for the ester esterification over here. So conditions for the esterification. Now, one is we're using the concentrated H2SO4. There are two reasons why we use the concentrated H2SO4, the sulfuric acid. One is that this is using for the dehydrating agent. Now, have a think about what you mean by the dehydrating. Dehydrating simply means that we're removing the water from the system, isn't it? Yeah?
Yeah.
Now, Jenny, can you see the water on this side here, on your product side?
Yeah.
Now, think about what happened if we remove the water from the system.
Uh, if you remove water from the system.
Yeah, I'm basically removing this one out while reducing the amount of the H2O. Can we refer back to the Le Chatelier principle, which we learned in module 5?
So does it change the system?
Therefore, I mean, just simply talk about the shift. It will be shifted to where?
It is shifted to the left-hand side.
You mean the right-hand side?
Oh, sorry, right-hand side.
It shift to the right-hand side means what? We get more of those as that we produce to. So why are we adding some H2SO4? Basically, we want to induce the shift to the right-hand side. Therefore, we are able to get more yield of the ester. Does that make sense?
Yeah.
I'm talking about exam question style. This is very, very important questions that you need to memorize. And this is why I was quite upset when you started with the module 7 without the module 5, because it's limited how much I can explain without the module 5. But that's one reason why we do so. Second reason we're using the concentrated H2SO4 is basically, if you remember the H2SO4 effect, this part, I'm talking about this part over here. Can you see that? H2SO4 is helping out to break the bonds of the carbonyl groups. So it is working as a catalytic, or catalyst. So two reasons why we're using the concentrated H2SO4. One is as I said, the dehydrating agent, and another reason is that we tried to the dampening the activation energy required for the whole reaction process to work as a catalyst in that case. Make sense?
Yep.
Second, for the reflux, why do we use the reflux systems too? Now, the whole purpose of using reflux is, first of all, we want to recapture those volatile, like organic compounds. Now, volatile means what? Highly flammable. Highly flammable means it's highly dangerous. So this is why when you're performing the esterification, we're performing under the fume hood or in the open spaces using the condensers too. Now, recapturing the volatile organic compound has two main reasons. Now, have a think about in the given diagram here. If we can recapture them, so some of the gases would come out. Can you see, like, as we are hitting this up, they come out and comes out. If we do not have this condenser, basically what happens is they will be able to escape to the atmosphere quite easily too. So, in other words, we are able to lose some of our precious reactants without the reaction going through to produce the ester. So using the condenser of the reflux system, we are drawing those back into the system and let them just react it. So we just kind of squeezing the reactants until they fully get reacted using the condenser or the reflux system. So this is what we call the reflux. We're refluxing the whole like a reactants as well as the product back into the reactant site. So therefore we are able to maximize the yield of the ester as well too. So that's one reason. And so two reasons for these refluxes. One is for the safety reason that we don't want to release any of the volatile substance to the atmosphere or to the room. Secondly is the maximizing the yield of the ester. And same for that is basically the maximizing the yield of the ester as well too. Okay, so it's very important to know like what procedures we're going through, especially if you actually ever do like esterification in the schools. Highly likely you get a question in depth about esterification in your school exam in 2 weeks or week. So very important to understand like what the esterification is, the process, and time to times you need to memorize that actual esterification process as well too. So the method or the synthesis method would look like this. I should share my sample method with the safety issues. And I'll share this PDF at the end of the class so you can use that for your reference notes. So if you haven't done the esterification school, but most likely you will do it in a few weeks, this is basically the esterification process you need to know, and you need to actually memorize them. And I really mean like when I say memorize, you actually need to memorize the whole step-by-step of the step-by-step methods of the esterification, because time to time, especially with the scientific skill questions, there's a chance that they can ask you that, hey, what's the method of the esterification? Okay,
Yep.
so basically these are the or what I call the some general organic chemistry chemical reactions for now. So we're up to the ester. I mean, there are a little more like saponifications and some other polymerizations, but I don't think you get a questions up to there yet, especially the polymerization process. So what I do is I would just wait till you finish in the school to polymerizations, and it's important to know a few of the polymerization and polymers in details. But for now, memorizing up to 16 chemical reactions, especially for like production and usage of alcohol, this is up to here. Up to here is where you get your exams then.
Okay.
Quite a lot. So it means that, but as I said, like it's not so difficult in the organic chemistry term because I haven't actually touched like in module eight and come like combined yet too. That should be okay, to be honest. Like, I mean, I don't really see like these are hard questions. So in your levels, you should be able to do it without much problem,
Yep.
without much like difficulties. But any questions for now?
No, I'm good.
Okay. Share this PDF and share this video after the class so you can have a look at that and practice those questions that I gave you on Monday
Yeah.
and let's see how it
Oh,
goes. Like
are there
make it
any
a,
answers for those? The homework that you gave me?
I'm sure I printed the answers. If you cannot find the answers, let me know. I'll probably reprint you again on Monday then.
Okay.
Okay, that's all for today. I don't think we need any like extra classes for this unless you have any questions about your module seven content. So it's a matter of that you practice it
Yeah.
up to here, and it's matter of like it's very important to know like actual physical property questions as well too. So if you have any questions, bring it on Monday. I'm happy to stay back a little bit and we can discuss the questions with you.
Yep. Thank you.
Okay, that's it. Bye.
Thank you.